Imagine standing at the edge of a cliff so deep that if you dropped Mount Everest into it, the peak would still be buried under more than a mile of ocean water. Now imagine that this place is real. It sits at the bottom of the Pacific Ocean, wrapped in absolute darkness, crushed under a pressure so intense that it would flatten a submarine like a tin can. This is the Mariana Trench, the deepest scar on the face of our planet. And its story is not just about depth. It is about the very engine that built the world we live on. For centuries, humans believed the ocean floor was flat, a featureless plain of sand and silence stretching from continent to continent. There was no reason to think otherwise. No one had ever been down there. No instrument could reach that far. The ocean was simply a mystery. And then, in 1872, everything changed. A British Royal Navy ship called the HMS Challenger set sail on a mission that would rewrite our understanding of the Earth. The expedition was ambitious, spanning nearly 4 years and covering almost 70,000 nautical miles. The crew was not searching for treasure or new lands. They were searching for knowledge, and they carried with them the most advanced technology available at the time: rope and lead weights. It sounds almost laughable now. But back then, measuring the depth of the ocean meant lowering a heavy weight on a long line and waiting for it to hit the bottom. The process was painfully slow and wildly imprecise. Still, off the coast of Guam, roughly 200 miles from the island, the crew lowered their sounding line into the Pacific. And it kept going, and going, and going. When the line finally stopped, the measurement read nearly 5 miles. 5 miles straight down. The crew had just discovered the deepest point anyone had ever recorded on Earth, and they had no idea what had created it. That discovery sat largely unexplored for decades. The technology simply did not exist to investigate further. But in 1951, a second British vessel, the aptly named Challenger 2, returned to the same waters. This time, the ship carried sonar equipment, a technology born from the urgency of 2 world wars. Instead of ropes and weights, sound waves were fired into the deep, bouncing off the ocean floor and returning with data far more precise than anything before. What the sonar revealed was staggering. The Mariana Trench was not just a deep hole. It was a massive geological feature stretching nearly 1,500 miles across the Pacific. That is roughly the distance from New York to Denver. And at its deepest point, a place now known as the Challenger Deep, the floor plunged to nearly 7 miles below the surface, 30 times deeper than the height of the Empire State Building. The numbers were almost incomprehensible. But numbers on a screen are one thing. Someone had to actually go down there. On January 23, 1960, 2 men climbed into a vessel that looked more like a floating gas tank than a submarine. The Trieste was a bathyscaphe, a deep-sea submersible designed for one purpose: to survive the crushing pressure of the abyss. Inside, the crew compartment was a steel sphere barely large enough for 2 people. Less than 20 cubic feet of space. That is smaller than a phone booth. Don Walsh and Jacques Picard sealed themselves inside, and then they began to sink. The descent took nearly 5 hours. 5 hours of sinking through water that grew colder and darker with every passing minute. The temperature dropped toward freezing. The pressure outside the hull climbed relentlessly. At the halfway point, the weight pressing against the Trieste was already beyond anything most engineered structures on the surface could withstand. And they were only halfway down. Then, at around 30,000 feet, something happened that could have ended everything. A sharp crack echoed through the tiny compartment. The outer viewing window had fractured under the pressure. Inside that sphere, with miles of ocean above them and miles of darkness below, the 2 men had to make a decision. They chose to keep going. When the Trieste finally touched the ocean floor at a depth of 35,814 feet, Walsh and Picard looked out through their small porthole and saw something no one expected. Life. A small flatfish, pale and ghostly, drifted across the sediment. At a pressure exceeding 16,000 pounds per square inch, roughly 1,000 times the pressure at sea level, a living creature was calmly going about its existence. The deepest point on Earth was not lifeless, it was inhabited. But the real revelation of the Mariana Trench was not about the life found at the bottom. It was about what the trench itself tells us about how our planet works. To understand that, we need to look at the Earth not as a solid rock, but as a machine. A slow, massive, incredibly powerful machine that has been running for billions of years. Beneath the thin crust we live on, the Earth is anything but still. The planet's interior is a furnace of molten rock and intense heat, and that energy does not simply sit there. It moves, it circulates, and it drives the most fundamental process shaping our world: plate tectonics. The surface of the Earth is broken into enormous slabs called tectonic plates. These plates are not fixed, they drift, they collide, they pull apart. And the Mariana Trench is the single most dramatic example of what happens when two of these plates meet head-on. On one side, you have the Pacific Plate. It is the largest tectonic plate on Earth and also one of the oldest. The rock on the Pacific Ocean floor near the trench has been dated at roughly 170 million years old. That is ancient by geological standards. And over those millions of years, the plate has cooled, contracted, and become incredibly dense. Think of it like a piece of bread left out for days. It started soft and light, but now it is hard and heavy. On the other side sits the Philippine Sea Plate, a smaller and younger plate. When these two collide, there is no contest. The older, heavier Pacific Plate is forced downward, diving beneath the Philippine Plate in a process called subduction. And as it plunges into the Earth's interior, it drags the ocean floor down with it, creating the Mariana Trench. This is not a gentle process. The Pacific Plate descends at an angle, grinding against the edge of the Philippine Plate as it goes. The forces involved are beyond anything we encounter in daily life. The scale is continental. The time frame is measured in millions of years. And the result is a gash in the ocean floor that reaches nearly 7 miles deep. But the trench is only one part of the story. As the Pacific Plate sinks deeper into the Earth, it carries with it water, sediment, and minerals from the ocean floor. When this material reaches a depth of roughly 60 miles, the heat and pressure become so intense that the rock begins to partially melt. This molten material rises back toward the surface, and when it breaks through, it creates volcanoes. About 200 miles west of the Mariana Trench, a chain of volcanic islands rises from the sea. These are the Mariana Islands, and they owe their existence entirely to the subduction happening in the trench. Every eruption, every new island, every volcanic vent on the ocean floor nearby is a direct consequence of the Pacific Plate being consumed by the Earth's interior. The trench and the volcanoes are two halves of the same system. One destroys crust, the other creates it. And here is where the story gets truly fascinating. For decades, scientists believed that plate tectonics was driven by the upwelling of magma at mid-ocean ridges. The idea was simple. Hot rock rises at the ridges, pushes the plates apart, and that force drives everything. The ridges were the engine. The plates were just passengers. But the Mariana Trench helped overturn that entire model. What researchers discovered is that the real driving force of plate movement is not a push from behind. It is a pull from the front. The cold, dense edges of tectonic plates at subduction zones like the Mariana Trench are so heavy that they sink into the mantle under their own weight, dragged down by gravity. And as they sink, they pull the rest of the plate behind them, like a heavy tablecloth slowly sliding off a table. The magma at mid-ocean ridges does not push anything. It simply fills the gap left behind as the plate is pulled away. The ridges are passive. The trenches are the real engines. This was a complete reversal of the prevailing theory, and it changed the way geologists understand the forces that have shaped every continent, every ocean, and every mountain range on the planet. The Pacific Plate moves faster than any other plate on Earth. And the reason is simple. It is surrounded by subduction zones. The Mariana Trench to the west, the Tonga Trench to the south, the Aleutian Trench to the north. Each one is pulling the plate in its direction, accelerating its movement. The Pacific Plate is essentially being dragged across the planet by its own sinking edges. Now, one of the most puzzling features of the Mariana Trench is what it does not produce. Unlike other major subduction zones around the world, the Mariana Trench has never generated a catastrophic mega-earthquake. The subduction zone off the coast of Sumatra produced the devastating earthquake and tsunami of 2004. Alaska's subduction zone generated a massive quake in 1964. Japan's produced the event in 2011. But the Mariana Trench? Relative silence. For years, this was a mystery. How could the most active subduction zone on the planet, consuming more crust than any other, remain so seismically quiet? The answer came from an unexpected source: mud volcanoes. Scattered across the seabed near the trench, researchers found strange mounds that were not erupting lava, but thick, mineral-rich mud. When they analyzed the composition, they found it was made primarily of a rock called serpentinite. This is a soft, slippery mineral that forms when ocean water reacts with certain rocks in the mantle under high heat and pressure. Serpentinite acts as a natural lubricant. It coats the boundary between the two colliding plates, reducing friction and allowing them to slide past each other smoothly rather than locking up and building tension. In subduction zones without this lubrication, the plates grind and stick, accumulating enormous stress until they suddenly snap, releasing energy as a massive earthquake. At the Mariana Trench, the serpentinite prevents that buildup. The plates glide, the tension dissipates, and the region remains remarkably quiet. This discovery had enormous implications for understanding earthquake risk around the world. It showed that the composition of the rocks at a subduction boundary could determine whether a region experiences devastating quakes or remains stable. It was a piece of the puzzle that scientists had been missing for decades. Deep within the trench itself, there is another feature that defies easy explanation: the Challenger. Deep, the absolute lowest point sits roughly 11,000 meters below the surface. But it is not simply the lowest point of a gradual slope. It is an additional plunge of nearly 10,000 feet below the surrounding trench floor. A hole within a hole. Scientists believe this extreme depth is caused by a tear in the subducting Pacific Plate itself. As the plate bends and descends, the stress of the angle can cause it to crack. When a section of the plate breaks free, it drops nearly vertically into the mantle, displacing the material below it and creating an even deeper cavity. The Challenger Deep is essentially the result of the Earth's crust ripping itself apart under its own weight. The rocks recovered from the floor of the trench tell their own story. At 170 million years old, they represent the oldest oceanic crust on the planet. This is the rock that has traveled the farthest, cooled the most, and become the densest. It is this extreme density that explains why the Mariana Trench is deeper than any other. The older and heavier the crust, the deeper it sinks when it enters a subduction zone. And all of this, the trench, the volcanoes, the earthquakes that do not happen, the mud that lubricates the plates, is part of a single global cycle. The Earth's crust is born at mid-ocean ridges, travels across the ocean floor for millions of years, and is eventually consumed at subduction trenches. It is recycled back into the mantle, melted down, and eventually returned to the surface as new volcanic rock. The Mariana Trench is the largest recycling center on the planet. Scientists estimate that it consumes an area of ocean floor equivalent to the size of the continental United States roughly every 4 million years. And this process has consequences that reach far beyond the ocean floor. The Pacific Ocean is shrinking. Every year, the subduction zones around its edges consume slightly more crust than the mid-ocean ridges produce. The net result is that the Pacific is getting smaller by roughly 3 inches per year. That does not sound like much. But over millions of years, those inches add up. If the current pattern continues, geologists project that the Pacific Ocean will eventually close entirely. Australia, which is currently drifting northward, will collide with Asia. The Americas, pushed westward, could eventually meet the land masses on the other side. The entire geography of the planet will be reshaped. Continents that are currently separated by thousands of miles of open ocean will be pressed together, creating new mountain ranges, new coastlines, and a world that would be unrecognizable to anyone alive today. This is not speculation. It is the logical extension of processes that have been operating for billions of years. Continents have collided before. Supercontinents have formed and broken apart multiple times in Earth's history. The Mariana Trench is simply the most visible evidence that this cycle is still running. And yet, for all we have learned, the ocean remains overwhelmingly unexplored. By most estimates, less than 5% of the world's ocean floor has been mapped in detail. The Mariana Trench, for all its fame, still holds secrets we cannot yet access. The pressures are too extreme, the darkness too complete, the technology too limited. We have sent more people to the surface of the moon than to the bottom of the Mariana Trench. We have more detailed maps of Mars than we do of our own ocean floor. The deepest point on our planet, the place where the Earth's most powerful geological forces are on full display, remains one of the least understood places in the entire solar system. The Mariana Trench is not just a geological curiosity. It is the keyhole through which we can glimpse the machinery that runs our planet. Every continent we stand on, every ocean we sail, every earthquake we feel, and every volcano that erupts is connected to the same forces that carve this trench into the floor of the Pacific. It is a reminder that beneath the thin, fragile surface we call home, the Earth is alive. It is moving. It is changing. And it has been doing so long before we arrived, and it will continue long after we are gone. The deepest point on Earth is not just a record in a book. It is a window into the past, a warning about the future and proof that the planet beneath our feet is far more powerful, far more dynamic, and far more mysterious than most of us will ever realize. And we have barely scratched the surface.